Okay, so chemical equations. Here we go. You've almost certainly seen these things before. But a chemical equation. Lots of these blanks are going to be redundant, and that's okay. A chemical equation is just like a math equation. It is a statement. It has a lot of meaning built into it, and it uses a bunch of different kinds of symbols. So a chemical equation is a statement that uses words or symbols to describe a chemical reaction, very similarly to how a math equation would work. It describes the chemicals that you start with, also called the blank, and those that are produced after the reaction has taken place, also called the blank. The produced ones, I mean, they make a lot of sense. If you make something, if you have produced something, that thing is called the what? You have a product. You have produced a product. So the product is what's coming out the other end. That's the second blank there. And the thing that you go in, the things that you allow to react, we call those the reactants. That's this blank back here. So our symbology is a little different than math, but the ideas are the same. We start with the chemicals, and we're going to use the names or the formulas for those that are reacting. We put an arrow in between them to indicate the direction that the reaction is happening in, which is actually more complicated than it looks, which is I'm going to demonstrate today. An arrow indicates the direction the reaction is happening in. What is reacting? And what is being produced. So a really simple version of a chemical equation would be this guy here. You've got reactant A, reactant B, you have product C, and you've got product D. And the symbols all have meaning. This plus sign in math generally means you're adding things, but in chemistry it means that one has reacted with the other. That arrow here means, the way we would read that is to produce. So reactant A reacts with reactant B to produce, or to yield is a word that we use there to talk about what comes out the other end. And it produces, or reacts to produce, products C and D, is how you'd read that thing. Now, as you guys go on in chemistry, you're going to see additions to this style of equation. Sometimes you're going to have an arrow that actually looks like this, where you have one on the top and you've got one on the bottom. And the chemical reaction can go both ways. And I'm going to demonstrate a reaction today that can do that because I've been looking for an opportunity to demonstrate this thing, just for fun. So sometimes you'll have reactant A and reactant B. They produce C and D, and then for whatever reason, the reaction slides back the other way, where your products from the first reaction become the reactants for the reverse reaction. You get stuff that looks like that. Because I've been looking for an excuse to do this, I'm going to demonstrate one of those things for you now. So, I've seen this done a bunch of times. It's a really cool reaction, but I've never actually done it myself. So, I need U6 to slide back, or just back. You should be good there. If you see purple gas forming, no, but back up. If we see purple gas forming, that's a problem.
Okay, gotcha.
Probably should be good.
I don't know like right now.
Yeah, right?
Yeah. No problem,
Okay. So this is an example. I've got three reactants here. I'll show you on the screen what's actually going on here. So this is the chemical equation for the reaction that I'm about to do. I'll put that guy up there at the top. And I mean, the one that I just gave you, reactant A plus reactant B produces product C and product D, is a little bit less complicated than this one. But I mean, the ideas here are the same. This one has 1, 2, 3, 4 reactants, and it produces 3 different products. And in this particular reaction, as these products build up, you're actually going to see this reaction get pushed back the other way. And then as these products build up from the reverse reaction, it's going to get pushed back the other way. And then these are going to build up, and it's going to push back the other way. And it should, if I do it right, bounce back and forth here for 5 or 10 minutes. So, I need 300 of this guy. Let's change it. 300 you. Cool. Okay, let's see if she works. There we go. Nice. There we go. So this reaction, as you see on the screen, it's called the Brigg-Roscher reaction. Sometimes called the Brigg-Roscher plot. It's a demo I've wanted to do for a long time. I've seen it a few times. It's really quite a cool reaction. And it's just all that's happening there is as like I said, as these as these products build up, it forces the reaction back the other way. Why you getting on? And if you can see, the first two things that I added together were colorless. The third thing I added, I think, was also colorless. But these products are. And now this thing is it'll oscillate. Oh, there you go. This thing will oscillate now by itself for a good 5 or 10 minutes. So you can just kind of let it sit while I keep going. Yeah. So there's all sorts of cool little reactions that you can do like this. I'll get you guys to demo some, or do some in this lab as well. This one's a little bit more dangerous for reasons. So yeah, I don't know, cool reaction. Questions, comments, concerns about this? Then always let it sit and go. Yes. The different products are different colors as the thing slides around. So I do. It's a complicated reaction to explain, but I'll do my best. Whoops. Okay, so how's the color changing? The reaction is that guy. Okay. And there's actually going to be a fourth color produced here in a little bit, and when that fourth color shows up, that's when this thing is. Okay, so so in this big long reaction, there's actually two kind of sub-reactions that are happening. One of the sub-reactions involves this guy, the iodine trioxide. This guy's called hydrogen peroxide. And this guy is the pure hydrogen. These three guys react first to produce pure iodine, I2. And in that process, so these guys are reacting, and one of the products out of these, as these three react, is just pure I2. Because what's happening here is you get this H2O2, you've got the O's from the iodine trioxide, and you've got this pure hydrogen. Those three things are reacting. This guy, and this guy are actually producing water. And that guy is breaking up the iodine. The iodine, when it bonds together, is yellow. The navy blue shows up as the iodine builds up. As the iodine builds up, this guy starts to produce. The iodine reacts, the I2 reacts with this piece here. The iodine reacts with this guy. And it's the iodine reacting with this that produces that blue, now it's almost black color. And then as the iodine builds up with this guy, and these two things show up, you see it bubbling. This is oxygen gas being produced. Yeah, now we're at this stage. As that builds up, come on, go again. Yeah, it's slowing down. It forces the reaction back into the individual products here. And that's why it was clear for a second. And then once these four things all show up again, you get that guy, and that guy reacting together to produce your yellow. Then the product of the yellow reacts with that guy to produce the blue. Yes. Make sure I answer that properly. It needs to be stirred because as these guys are being produced, so as that middle reaction is being produced, it's getting produced, like the reaction's happening all throughout this liquid. And so what you want to make the reaction continue to move back and forth, you want to make sure that there's an even distribution of all of what's being produced kind of throughout the entire stack of liquid. So we keep it stirring so that the reaction, like if I didn't stir it, it wouldn't necessarily continue to slide back and forth, but the concentrations wouldn't be uniform throughout the mixture. But there's another reaction that I'm hoping to show you guys next week. You've seen her, she's the hall lady, she's here on Tuesdays in the lab sometimes. Her name is Christy. She's our lab tech, she works with us and Basin and Moet. And there's a reaction like this one that she's actually wanted to do for a long time. And she wants me to demo it because I like to do these kinds of things. It isn't mixed. That one it goes one way, kind of all by itself. If we can get it working, I'll show it to you guys. The reaction goes kind of all one way by itself and then stops, and then you actually have to take a pan and you shake the pan, and it forces it to mix again, and then it'll restart and go from it starts kind of an orangey color and then all fades to about this color blue. But the process of it fading is pretty dramatic. It's cool. It fades to blue, and the whole pan becomes blue. You shake the pan, the whole pan rapidly turns orange again, and the whole thing goes again by itself. There we go. That's that. That's what we want.
Okay, that's been that color.
No, it's not the color, it's the gas.
Oh.
That's what we want. That purple gas is that. Purple gas. That purple gas is, it is an iodine compound. And iodine compounds on their own are actually quite potent. So that particular iodine compound is what I'm trying to waiting to see, I'm trying to avoid. And so what I'm adding now is called sodium thiosulfate. And it actually bonds with the iodine in there that's being produced. And so you can see that there's no purple gas up at the top anymore. And I've effectively killed the reaction. The reaction isn't going to continue anymore because this extra reactant bonds with the I2 that was produced, prevents that gas from forming and actually kills this process. Let's see more. Purple is one of the prettiest colors in chemistry. If purple shows up on something that you're working with, that's a problem. Nice. And the reaction actually got very hot. There we go. So this reaction really serves no other purpose than looking cool. There's nothing special about this thing. It's one of the things that people had figured out how to play with, that this reaction kind of exists. But again, it serves no other purpose. And there's things that you can change. So like this, just because this is the reaction that we've done, it's not the only way to do this particular reaction. You can actually swap out this guy right here. This is called a starch. And you can swap out that starch for a fluorescent dye so that this thing actually glows under UV light in the dark. There's a bunch of different ways that this reaction can show up. Any other questions? I think it's a cool reaction. It's one I wanted to do for a while. There we go. As soon as it stays colorless, we're done. So much of what, sorry? It's actually put in a lot less than I was supposed to do the reaction. I don't necessarily, I don't know why this is taking so long to reduce. But it will. Yeah, and the reaction, so it wasn't steaming before. But this reaction is quite hot right now. Cool. So I'm going to pull this over to the side, I'll put it next to my desk, so if anyone gets poisoned, it's going to be and we'll keep an eye on it, but we're going to keep going. If anyone sees that thing turning purple again, let me know. Because that's a problem. Okay, there we go. So, the Brig Rusher clock is what that thing's called. Love it. Okay, I think so too. So chemical equations show up in a bunch of different ways. As you can see, that one was pretty long. It had 4 things on one side, 3 things on the other side. All those things have different names. I can show you what those names are, but it gets kind of cumbersome to put it down. That's why we go through this whole process of trying to figure out how can I write the formulas for these various compounds, because it takes up a lot less space and it's a lot easier to communicate some of those ideas. So the first way we can demonstrate these things is by using what's called a word equation. This is a really simple one. Magnesium reacts with oxygen to produce magnesium oxide. The things on the left are always your reactants. This one only has an arrow that goes one way, and it reacts to produce magnesium oxide. These are the products. This is a simple reaction that happens kind of all the time. Like in the chemical storage room, we have ribbons of magnesium. They're ribbons of magnesium. You guys are I'll demo them. You guys will get a chance to burn them yourself. Perhaps you've seen magnesium ribbon get lit on fire before. It produces this very bright white light that you're not actually supposed to look at. But until you actually do something with the magnesium, it just sits there in the jar. The jar is not airtight. It's open to the atmosphere, and so the oxygen from the air starts to react with the magnesium strips that you have that's stored in the chemical room, and it's producing this slowly and constantly over the entire outside. You've seen reactions like this happen before. If it's not magnesium, maybe it's iron. If iron reacts with oxygen, what are you producing? What's that called? That process. We give it a name. 4 letters, starts with an R. It's reddish. Rust. So iron, pure iron, will react with oxygen to produce rust. It's the same idea. Effectively, what this reaction is, it's the rusting of magnesium. Silver does this as well. If you've ever seen, like if you have a grandma or whatever with silver, we call it silverware, spoons and knives and forks that are made of silver, they tarnish. They turn a kind of a dark gray or black over time. That's what's happening here. They're just reacting with the oxygen and producing something new, a layer over top. So that's a simple one. The word equations for larger equations, like the Brigg-Rasher clock, get pretty wordy, and so that we take the names and we reduce them down to their chemical formulas, which is why we spend so much time in grade 9 and grade 10 building that skill. And we build what's called a skeleton equation. What's a skeleton? If you had to describe a skeleton to someone who didn't know it, Evelyn, how would you do it? Without any added what? I felt like you were going to finish an idea. Okay, forget chemistry for a second. What do you think of when I say that word skeleton? Of what? So when I say the word skeleton, you think of chemistry. Okay, what do you know? Like what do you actually? I say skeleton, you think. What's the first picture you get in your brain? Bones. Okay. And what if I took a set of bones and I assembled them in a particular way? You go to the pump house. Mr. Lackold has a full-blown skeleton in the corner. Hands up if you've seen it. You mean if you've seen it? What's that a skeleton of? It's a person. And you can tell based on looking just at the bones, how they're assembled, that thing was at one point a human being. If you go to Science World, hands up if you've been to Science World. You walk into like the first exhibit on the right-hand side with all the other animals. There's something big in the back. What is it? Yes, which one? Who said dinosaur? It's a T-Rex. And you know that based just on the fact that it's bones. That thing isn't going to function, thankfully. It's not going to come to life in Science World. Mr. Lackold's skeleton of a person isn't going to come to life in the pump house. But based on the bones alone, you know what you're looking at. And so a skeleton equation is exactly the same idea. It doesn't have all of the information that's present. It doesn't have all of the necessary pieces that are there for it to function the way it should. But a skeleton equation provides you with an idea of what's going on. A pretty good one. If I walked a human skeleton in here, you'd know it was a person. If I changed the forehead a little bit, you'd be like, that looks like a human, it's not a human, and I would say you're right, it's actually a chimp. So, like, the subtle changes that we provide in the skeleton actually are enough to tell you what you've got. And so another word for a skeleton equation in chemistry is what's called an unbalanced equation. And I'll talk about why that is. So, skeleton equations is this first blank here. Provide the chemical formulas for the reactants and the products, but does not necessarily follow the law of conservation of mass. So, we did a reaction in a lab yesterday and the day before. You guys, in a closed system, you allowed two things to react. There's still some of them sitting over there on the side, and I told you about it. You guys verified it. The law of conservation of mass is a thing. All of what's there at the beginning needs to be all of what's there at the end in a closed system. Is that what's happening here? Here's another. I've taken the magnesium, reacts with oxygen, produces magnesium oxide, and I distilled it down to the individual chemical formulas. Magnesium is just Mg. Oxygen on its own, you guys have seen when you were doing Bohr diagrams and Lewis diagrams, that oxygen on its own makes O2. When you react the magnesium with the oxygen, you also saw when I was getting you guys to write formulas for the names of things, that magnesium has a charge of +2, oxygen has a charge of -2. So when you swap and drop and reduce these things, you produce MgO. But does what we've written down here for the skeleton equation follow the law of conservation of mass? How many magnesiums do I have on the left? I got one of them. How many oxygens do I have on the left? I got two of them. How many magnesiums do I have on the right? One of them. How many oxygens do I have on the right? One. So this thing, because I've only got, here I've got one oxygen. Here I've got two oxygens. This particular skeleton equation does not, I'll do it this way. This here means this thing is unbalanced. We know that magnesium on its own reacts with oxygen, and on its own we know that oxygen is O2. We know that they produce MgO, but the proportions are off, the ratios are off for these things. And so we need to figure out what's actually going on. When you're ready, flip the page. The figuring out what's going on here is going to take us the better part of almost a week, just because there's going to be a lot of practice involved. So when you're ready, flip the page. Skeleton equation is good, gives you an idea of what's going on, but a skeleton equation doesn't give you the full picture. It doesn't tell you in what amounts these things react. It doesn't tell you in what amounts these things are produced. And so we need to make sure that we need to be able to go ahead and figure out what those proportions are. Because if you go into the lab and you just start mixing stuff together, sometimes what you produce is a lot more than what you were expecting based on what you put in. So according to the law of conservation of mass, atoms cannot be created or destroyed. In a chemical reaction, they just get moved around. They can be created and destroyed other ways in physics, but not in chemistry. Chemistry obeys the law of conservation of mass. So in a balanced chemical equation, the same number of atoms of each element must be present on both sides of the arrow. Nice, that thing is done. We'll leave that blank for a second. Here is an example of a fully balanced, of that same equation, fully balanced before. So above it, I'm just going to write down the equation that we had. We had Mg plus O2, we had the arrow, and we had MgO. That was the unbalanced skeleton equation that we had before. And if we were to go ahead and actually fully balance this thing, what we'd see is this. We would see that we've now got, or now that we need 2 mgs plus an O2, and it's going to react to form 2 MgOs. These values right here, that guy, the missing one there, and that guy there, have a name. I guess it's on the page and you can read it, but it's the same name that we give to those same numbers when they show up in front of variables in math. You guys are all in Science 10, which means you've all done Math 9. I mean, it might have been introduced to you in middle school as well. It's the same idea as what you've got in math. When you have a number in front of a variable in math, what's that thing called? It's called a coefficient. And the coefficient does what job? What's the purpose of that number out front? To show you that there's more than one of something. If there is no coefficient in front of a letter, how many do you have? You've only got one of something. All of those rules are the exact same thing here in chemistry. So what this is telling us is that these are coefficients. That's this blank right here. We add coefficients, coefficients. This is achieved by using coefficients in front of the elements and compounds in the reaction, present in the reaction. So the skeleton equation, the individual pieces of the skeleton equation do not change. Mg is Mg is Mg. It's on its own, it's fine. O2 is O2. Doesn't change, it's left alone. MgO doesn't change. We know that when magnesium and oxygen react, they produce MgO. It just is this way. And so if we wanted to change the numbers that are present here, we can't change any of these individual pieces. I can't just make this O, just erase the 2, and I see students try this all the time. It's just Mg plus O. Now it works. Well, you can't do that because O doesn't exist. O2 exists, and so that's what we need to work with. And so we add these coefficients out front to modify this thing, and now we can actually go ahead and count and see what we've got. The each Mg represents an atom of magnesium, and so by putting a 2 out front here, now I've got 2 atoms of magnesium. 2 atoms of Mg. Magnesium, just on its own, doesn't bind together. It just kind of clumps. It just is present together. O2 is a different animal. Why do we call this thing O2? Think back to our Lewis diagrams. Why is O2 O2? Everything we're doing connects. Let's think back here. I'll draw it over here. Here's O2. A single lone oxygen looks like this with its outer shell. And oxygen wants to do what? It's going to combine with something. This is the reason why oxygen doesn't exist on its own. Oxygen doesn't exist on its own because it's desperately trying to fill these spaces for the electrons here. And so often the easiest way for oxygen to do that is just buddy up with another oxygen. I'm oxygen, you're oxygen, let's just hang out together. And when they do that, they share those electrons, those individual electrons, and now we have a stable compound. What kind of compound is this? Your options are either ionic or covalent. It's a covalent compound because the electrons are sharing. And one more piece, I gave you a name for covalent compounds. Another name for a covalent compound. It starts with an M. A molecule. This represents one molecule of oxygen. And one molecule of oxygen has how many oxygen atoms in it? 2. So that's what this 2 here represents. The fact that there is no, I put a question mark there. The fact that there is no number, just like in math, there is no number out front of the oxygen, that means that you have one what? You have one molecule of oxygen. And that little 2 there means that one molecule, it's a lot we're writing in here, of oxygen has 2 O's, or 2, I'll say atoms. Atoms. Tweak, I'll change that. Sorry, my bad. 2 atoms of O. So I've got 2 atoms of magnesium. I've got 1 molecule of oxygen. That 1 molecule of oxygen has 2 atoms in it. And when they react, they produce MgO. And, well, 2 of them. 2 magnesium oxides. And if we go ahead and count this thing, how many atoms of magnesium do I have on the left? 2. How many atoms of oxygen do I have on the left in that 1 molecule? 2. That little subscript there tells you that every molecule has 2, and I've got 1 molecule. So I've only got 2 atoms. And then over here, each MgO, magnesium oxide, has 1 magnesium and 1 oxygen. But that 2 out front means now I have 2 groups of Mg and O. So how many magnesiums are present here? 2. And how many oxygens are present over here now? 2. 1 in each MgO, but I've got 2 MgOs. So on the left-hand side, I've got 2 magnesiums. On the right-hand side, I got 2 magnesiums. On the left-hand side, I've got 2 oxygens. On the right-hand side, I now have 2 oxygens. So this equation is now what we call balanced. There's the same number of atoms on both sides of the equation. And so now this obeys the law of conservation of mass. If you were going to go into the lab, you would need to provide twice as much magnesium for the same amount of oxygen gas. Right, when you build this guy, you have to follow the balancing that we did before. Mg and O, they're going to react a particular way. The charge on magnesium is +2, its oxygen is -2. One of each will show up and they will be stable. So you do not ever change the chemical formulas for what's here. You build these chemical formulas the same way we built them 2 weeks ago. That hasn't changed. The only numbers that you're allowed to change out front here are these guys, the coefficients. You don't have that kind of chemistry bending power. And then in a full-blown, okay, I don't expect you to do this in your balanced equations, but in a full-blown balanced equation in all its gory detail, you're going to have these things as well. That guy, and that guy. And that's the last little piece of information. These letters tell you what state these individual things are showing up in. S stands for solid, G stands for a gas, L stands for a liquid. And then there's another one called AQ. AQ stands for this word aqueous, and what that means is whatever you have is dissolved in water. So for example, where's the one from yesterday? This guy. In the lab that you guys did for me yesterday, that clear bottle has NaOH in it. But sodium hydroxide on its own is not a liquid. Sodium hydroxide on its own is a crystal. This is an ionic compound. Na is +1, OH is -1 when that's a solid. This one's weird. When they react, they form a crystal. You can take that crystal, pour it in water. So you would table salt, you NaCl. On your table, it's a crystal. You pour it in water, it dissolves. So NaCl can show up as a solid, or NaCl can show up as a cube. This is what you have on your table. This is what it disappears into when you put it on a cucumber. Dissolves in the water. That's all that symbol means, what these letters mean. And so these letters become really, really important. NaOH, this is the same thing. This brand of NaOH would be technically, if I'm in this full gory detail, would be NaOH-AQ. And then I don't know if any of you stopped to read this bottle. There are then numbers on the side of the bottle. This one says 0.1 m. It tells you how much NaOH is actually dissolved in the water. And this is a huge part of, like, figuring out these values is a huge part of what you'll do in chemistry 11. Yes. AQ means it's dissolved, yeah. There are only 3 things, to my knowledge, that show up with an L next to them. The first one is water, because AQ is defined to be something dissolved in water. And so water cannot be dissolved in water. Water just is, right? And so water shows up as an L. And then if you look at the periodic table up the one on the left, actually both of them have it. There's 2 elements up there that are listed blue. One of them is mercury, one of them is bromine, and what that means is that Hg and Br at room temperature on their own are both liquids. So those guys would show up with an L as well. Just because you dissolve them in water doesn't make you a liquid. It makes you an aqueous solution. To be a liquid, you actually have to be melted. You have to be molten. So, let's go play with this. Quick atom counting review. Let's make it more interesting. So, here we go. I've got this. I've got 5 H2Os. That 5 out front is the coefficient. If I cover up the 5, you still know what's there. H2O is H2O, it's water. Dihydrogen monoxide. The 5 out front means that I've now got 5 molecules of water. That coefficient 5, describes, and it's what I was saying before, but we're going to formalize it here. That 5 out front represents the amount of molecules and any subscripts. In this case, there's only one subscript, the subscript. I'll say the subscripts. Describe the number of atoms of the element in front of them in each molecule. So that little 2 there tells you that there are 2 hydrogens present. The fact that the O doesn't have a subscript means how many oxygens are present? 1. If there's no subscript and there's no coefficient, that by definition means there's 1 of something. So to count the total number of hydrogens here, what do? There's 2 in 1 molecule of water, and I have 5 molecules of water. So to figure out how much hydrogen is present, what do? Evelyn, you multiply them together. 5 molecules times 2 atoms per molecule is going to give you 10 atoms of hydrogen. How many oxygen atoms are there? Well, each water has how many? 1. And how many water molecules are there? 5. So 5 times 1 equals 5 oxygens. Oxygen atoms present in that 5 H2Os. Let's do another one. Let's make it more interesting, because these compounds get large, and so let's give you a bigger example. I've got this guy here. I've got Ca3PO42. Ignore the coefficient for a second. I'm going to remind you guys where this thing came from. Where did Ca3PO4 come from? Well, Ca, if you recall, is it's calcium. It's a metal. It's got a charge of +2. It's in the same family magnesium's in. And PO4 is a polyatomic ion. It's phosphate. Phosphate's got a charge of -3. So this PO4, charge of -3, and we're going to react the calcium with the phosphate. How we do that doesn't matter, but we will. When we react these things together, because this is an ionic compound, they come together a very particular way. I told you guys at the beginning when we were putting these things together, reviewing ionic compounds, that ionic compounds show up, they react and follow two rules. They balance charges, and they do that in the lowest terms. So the smallest number that 2 and 3 both go into is 6. So if I wanted to get to 6, a charge of 6, positive and negative, I would need how many calciums to get to 6? 3 of them. And how many PO4 groups would I need to get to 6? I would need 2 whole groups. And so if you recall, for the polyatomic ions, we throw the brackets around the entire polyatomic ion, and then the subscript that we need goes outside of that to bring the entire group. So that's where Ca3PO4 came from. And now somehow I have 5 of them. So when we go ahead and count all of the individual pieces, one piece of the compound had 3 calciums, but now I've got 5 of those things together. So how many calciums do I have total? I have 15. 5 times 3 equals 15 calcium atoms. The polyatomic ion on its own, PO4, had 1 phosphorus and 4 oxygens. But when I built the compound, I had to put a 2 outside here because I needed 2 groups of phosphate. When I built the thing and brought 2 PO4s, how many phosphoruses did I have? Each polyatomic ion had 1, and now I need 2 groups. So there's 2 phosphoruses here. And how many oxygens were here? Each phosphate has 4, and I needed 2 groups of them. Yeah, 4 times 2 is 8. But now I don't have 1 Ca3PO42, I have 5 of them. So the original phosphate had 1 times 2 is 2, but now I've got 5 of them, so 1 times 2 is 2, times 5 is 10. You multiply all the way out. I had 1 times 2 times 5 phosphoruses. So that's a total of 10 phosphorus atoms. And the oxygens. 1 ion of phosphate had 4. 2 ions of phosphate will have 8, because 4 times 2 is 8. And now if I've got 5 groups of 2 phosphates, I've got 4 times 2 times 5. 4 times 2 is 8 times 5 is 40 oxygen atoms. And so that's how you count these things. Questions, comments, concerns about what I've just done? I know it's early morning on a Thursday. Yes, Brooklyn. Why was there 2 phosphoruses? Because when I built this thing, I had Ca, I had calcium, and I had phosphate. An individual phosphate only has, there's no subscript, that means there's 1 of them. But then to balance the charges on the calcium and the phosphate, I had to, effectively I swapped and dropped here. So what originally had 1 phosphorus in a single phosphate ion, I needed 2 phosphate ions. So if each phosphate has 1 phosphorus, and I brought 2 phosphates, now I've got 1 times 2 is 2 phosphoruses. It's the unwritten subscripts that tend to screw with people. Are we cool with the calciums and the oxygens? Okay. Let me show you why I'm making you count things. Flip the page when you're ready. Here we go. I want you to count things because now you have to go out of your way to start to try and figure out how to balance these things. You guys need to play the chemist and say, well, if I start reacting these things together, I know what they're going to produce because they're going to follow the rules laid out in ionic bonding. If I have magnesium and I have oxygen, I'm going to put them together. They're going to react. I know what they're going to make. They're going to follow the ion charge rules. But how much are they going to make? To balance an equation, what you're going to do is you're going to start with the chemical equation, and then you're going to add and change coefficients. You are only allowed to change the numbers out front. And you're going to do this until you have the same number of each atom on both sides of the equation. So this is a relatively simple one. I've got this guy, H2. H2 is what? Hydrogen. I've got O2, oxygen. And it's going to produce, when I react them, H2O. This is a really cool reaction because hydrogen on its own, does anyone know what hydrogen shows up as on its own? If I just had pure hydrogen, it's a gas. On its own, it's going to be a gas. Oxygen shows up on its own, it's a gas. And so there are schools that used to do this. Mowat used to do this. They have, it's actually pretty dangerous to have tanks of this at school, but Mowat does. We don't. We were never allowed to have these. Mowat does. They have tanks of hydrogen and they have tanks of oxygen. And what they would do is they would fill a balloon with hydrogen gas. Hands up if you've ever heard of the Hindenburg. No? No one of you have heard of the Hindenburg? Oh, say, have you heard of the Hindenburg? Yes? Okay. Yes. It was a blimp. Hindenburg. It's sad that you guys have not heard of this. Okay. Let me show you a quick picture of the Hindenburg and why we care about it as it relates to this demo. That's not the Hindenburg, that's my dog. Here's the Hindenburg. Come here, you. Okay. There's a reason we call it the Hindenburg disaster. Can you see that picture there? I know it's small. You see this picture? You see that gigantic fireball? No, this did not occur in Paris. So the Hindenburg, they were experimenting with different ways of flying people around. Planes were slowly becoming a thing, but people were like, balloons, guys! And so one of the things that they did was they made this blimp. You've seen blimps before, perhaps. The Hindenburg had a very thin metal shell, which is important, and it was filled with a gas lighter than air. Well, that gas they chose to use was hydrogen. Hydrogen is incredibly flammable, and metal is prone to sparking. And so they had this thing filled with a flammable gas, and the Hindenburg sparked. It blew up. It performed this reaction. So, and again, you can do this. W.J. Mowat has these tanks. We don't because it's dangerous. Mowat's an old school. Back before they cared about safety, they still have those tanks. Hydrogen, pure hydrogen, it's a gas, wildly flammable. Oxygen, very first day, we talked about safety. When oxygen is present, oxygen itself is not flammable, but it makes everything else wildly flammable. So you take hydrogen gas, you mix it with the oxygen, and if you provide a spark, it's explosive, as you saw in the picture. But when it explodes, it makes water, which is kind of cool. It just rains down everywhere. Mowat's actually, from what I understand, not allowed to do this anymore. What they would do is they would take a balloon of hydrogen and they would put it inside a garbage bag full of oxygen, and then they'd poke it with a flaming stick, and the whole thing would go boom, and it would shake the windows on the houses around W.J. Mowat. The explosion is that powerful. And then it just produces water. Like, it's an incredibly safe reaction once the products show up. But to get there, it's pretty dangerous. So we have to figure out in what proportions these things react. When you balance a chemical equation, throw the line down the page. to separate what's on the left with what's on the right. And then what we're going to do is we're going to list everything you have down to the atom on each side. So over here, we've got hydrogen atoms and oxygen atoms. And over here, we've got hydrogen atoms and oxygen atoms. Yes, I know they show up as water, but I don't care. We're not going to write them as water. We're going to write them as H and O. As it stands right now, before I've changed anything, in the skeleton equation, how many hydrogens are present? 2. How many oxygens are on the left? Also 2. How many hydrogens are on the right? 2. That subscript next to the H means I've got 2 hydrogens. How many oxygens are present? If there's no subscript, the number is a 1. So because these numbers are different between the oxygens here, this equation is not balanced. We have to now go ahead and balance this thing. You cannot, capital letters down there at the bottom, you cannot change the subscripts. Students try to do this all the time. Yeah, but if I just made this H2O2, it would be better. You're right, it would be. But it would be functionally different. When you react hydrogen and oxygen, it doesn't produce H2O2, it produces H2O. H2O you can drink, you get it from the tap. Does anyone know what H2O2 is? It's hydrogen peroxide. It's that thing you put on cuts. It fizzes. It's designed to kill stuff. You can't just change the subscripts because then you get something totally different. You cannot change the subscripts to balance the number of atoms. For example, H2 plus O2 does not make H2O2, even though this would balance it, because this changes the chemicals. It changes water into hydrogen peroxide. Hydrogen peroxide is designed to kill things. It's actually the single most dangerous thing we have in our lab here at Abbey is the pure hydrogen peroxide. It's insanely dangerous. If you go to the grocery store, you can only get like 3%. Maybe the most I've ever seen anywhere is 40%. But even that's pretty dangerous on its own. So let's go ahead and balance this thing. We cannot change the subscripts. We just have to change the coefficients. The hydrogens are already balanced, so let's go look at the oxygens. If I wanted to change this number out here, right now with no number present, there's a 1. I want to make these things equal. I want a second oxygen present. So what number could I put out front here to give me 2 oxygens on the right-hand side? Was that you? Yes, you're right. With nothing present, I heard someone say 1. With nothing present, the 1 is there already. So what we're going to do is we're going to change the coefficients. If I make this a 2, if I make this a 2 and now I have 2 molecules of water, that might solve my problem with the oxygens, right? Because look what I have here. Each water molecule has 1 oxygen, and now putting the 2 out front means how many oxygens do I have now? I got 2 of them. That's great. But now I've introduced another problem. Now there's 4 hydrogens. And so we're going to go and we're going to change the number. Every time you change the coefficient, you have to recount everything. By putting a 2 there, it gave me 2 oxygens, which I wanted. But now 2 water molecules is going to give me 2 times 2 is 4 hydrogens. So now my oxygens are balanced, but my hydrogens are not. So now we're going to go back and we're going to play with this number here. My oxygens are balanced. Don't touch this one. We're going to go play with that guy there. What could I do to my hydrogen molecules so that these guys would be balanced? Someone said it. Romina, was that you? I put a 2 there. If it wasn't 1 molecule of hydrogen gas, if instead it was 2 molecules of hydrogen gas, reacting with 1 molecule of oxygen gas to produce 2 molecules of water, 2 times 2 would be 4. My hydrogens would be balanced, my oxygen would be balanced. And so this is how hydrogen and oxygen actually react. I have 2 molecules of hydrogen plus 1 molecule of oxygen produces 2 molecules of water. And so now you have an idea of the volumes of these things that start to react. And the other piece I'm going to add in here is notice that there are no units here. I'm a math teacher, I'm a physics teacher, and I'm a chemistry teacher. So units to me are really, really important. There are no units on here. And so the same ratios would hold true for every unit. I talked about molecules of hydrogen, molecules of oxygen, and molecules of water. But we could talk about liters of hydrogen gas, liters of oxygen gas, and liters of water. If you had 2 liters of hydrogen gas, like a pop bottle full of hydrogen gas, 1 liter of oxygen gas, so 1,000 mils of oxygen gas, you mix those two together, you blew them up and let them react, you'd get a pop bottle full of water. A 2 liter of water would be produced from that explosion. And so this is where, at this stage, we're going to just do a bunch of this balancing stuff. In Chem 11, depending on who you have, I know Mr. Easton likes to get his students into the lab all the time. You'll do a bunch of this stuff. You'll do the balancing, and then he'll say, okay, cool, let's go into the lab and see if what you've predicted is actually going to be true. You'll balance the equations. You'll go into the lab and say, okay, well, I need 2 of this guy, and I need 3 of this guy maybe, and it should make 6 of something maybe. And so you'll go actually do the reaction, you'll weigh the products, and you'll be like, oh, look, I balanced this thing, and what I predicted was true. And so at this stage, it's an exercise in number crunching, which is going to feel tedious, kind of pointless. But once you get the handle on it, it actually leads to really cool stuff in the lab. Questions, comments, concerns about what I've done? I know the class is almost over, and you guys have been great today. I know I've said a lot of things. Okay, so I'm going to give you a couple tips for balancing. I'm going to give you a few questions to practice, and then tomorrow we'll do the bulk of the stuff. Here we go. Here's my tips. When you guys go and balance stuff, my first tip is this. Balancing involves trial and error. As a math teacher, I hate guess and check, but that's what you're going to be doing a lot of in this. Balancing in chemistry is going to involve a bunch of guess and check, and that's fine. Guessing and checking means you're probably going to get things wrong, means you're probably going to have to erase stuff, means you're going to have to start over. And so when you're doing this, my recommendation for you would be to use pencil, or I'm going to put something underneath, the whiteboard, because goodness knows we have a lot of them. That's 7 of them. Use the whiteboard to do the work when balancing these things. Now let's talk about the individual questions. Usually when you balance these things, you want to start left to right. Usually you want to start with the furthest left element and work your way to the right. In our case, we didn't do that because hydrogens were already balanced, so we moved to the oxygens. But as a general rule, you want to start with the first thing that's listed and work your way to the right, generally. If oxygen and hydrogen appear in several different formulas, leave them to last. And then if you're leaving oxygen and hydrogen to the very, very end, H is usually the absolute last. Absolute last thing you do. This next piece of advice, I'm going to star. And I'll come back to it because sometimes when I give this last piece of advice, it actually makes things worse for students. So I'm going to leave it blank for a second, but I'm going to add one more to the bottom here. I'll come back to that star for those of you who need it. Here's the last one. This might sound weird, but just write it down and I'll show you examples where this shows up. If odd amounts of oxygen cause problems. So if an odd number is causing you an issue, make it even. How do you make an odd number even? Nope, you don't add. Anyone who had me for math last year should know this. How do you take an odd number, make it even? There is one mathematical thing you can do. I'll tell you. Double it. And not just it, double everything you've done up to that point. Multiply everything by 2. And I will, it sounds weird to just write that down without having any sort of context, but I'll show you, I'll give you examples of where that plays out. Okay, so, you know what? I am not gonna do anymore. You have no homework from me. We will spend time tomorrow practicing this stuff. You've been great. When the bell goes, you may also go. Have a good day. We will revisit this tomorrow.